Hi class, welcome back to multivariable calculus. In this lesson, we are going to learn how to evaluate iterated integrals. So let's get started right away with an exercise. So here you see a double integral, and the way you read this is you have to look at your integral and your infinitesimal change in variable on the outside, like bookends. So from 0 to 1, this is going to be our interval for y, okay? So this would be 0 to 1 dy, and then for the inner bookends here, we're going from the square root of y to 1, and so that is going to be for our dx, okay? And so that's going to be our x interval, and our function is going to be the square root of 2 plus x cubed. And so I like to evaluate this. You're going to start with evaluating the inner integral, just as you would with, say, in like single variable calculus, in single variable calculus. And so in this one, you're integrating in terms of x, and then you're going to plug in and evaluate the limits afterward from square root of y to 1. And then you go through and you have to integrate then in terms of y. But the thing is, you're going to still have an x in there, and you're going to have a y in there, and you're not going to get a value out. So it's difficult to evaluate this integral in the form that it is currently set up in. So what we need to do is we need to put in some work here, and we need to switch the order of integration. To make it easier to evaluate. So what we want to do is we want the dy to be on the inside with the proper y extents, so we're going to have to adjust those, and we want the dx to be on the outside with the proper x extents. So we're going to let's go through the steps for doing this. So your first step is that you draw the region of integration. So in this case, we're going to have 0 is less than or equal to y is less than or equal to 1. Okay, so that's our extents for our y, 0 to 1. That's pretty straightforward. And then we have the square root of y is less than or equal to x is less than or equal to 1. And another way we could write this is that we're going from y equals 0 to y equals 1, and from x equal the square root of y to x equals 1. So what we want to do is we want to express y in terms of x. To reverse the order. Okay, so let's start out by plotting the region. Okay, so we have y versus x here. Okay, and here we have y equals 1. Here is y equals 0. Here is x equals 0. And here is x equals 1. All right. So now let's look at what our region R looks like. Okay, so here's the thing. As far as y is concerned, we're saying that we're going from 0 to 1. Okay, so 0 to 1 on the y. And for x, we're going from the square root of y to 1. And so it's going to be following the curve x equals the square root of y. One more time. So this is going to be x is equal to the square root of y. And to figure out which region we're integrating over, well, we're going from 0 to 1 for the y. And so we're going to have our boundary to the right of the curve here, and we're going to shade below. Okay, 0. So this includes 0 to 1 in the y shaded, and it also includes the square root of y, which is 0 here, all the way up to x equals 1 in the x. And another way to write this then would be that the curve is y is equal to x squared. Okay, so knowing this, we have to move on now to our second step. So let's continue. All right, so our next step is going to be that we create new limits of integration. Okay, and so we're going to have to express this first in terms of x. So looking back at our plot, in terms of x, we're going from 0, x equals 0 to x equals 1. So 0 is less than or equal to x, is less than or equal to 1. And then we have to set up our new limits of integration for y. And so for y, we're going from y equals 0 all the way up to y equals x squared. Okay, so now let's rewrite out our new integral. So we're going from 0 to 1 for x, and 0 to x squared for y, and we have the square root of 2 plus x cubed dy dx. All right, now we're on to our third step, and that, of course, is to evaluate. Okay, and so now let's start with this inside piece, so 0 to x squared, so the integral from 0 to x squared of the square root of 2 plus x cubed dy. So we're going to integrate that, so it's going to be, we're going to just keep everything on the outside as is, this 0 to 1 and the dx, so the integral from 0 to 1. Then we're going to evaluate the internal integral, which is actually pretty straightforward because it's the integral from 0 to x squared of the square root of 2 plus x cubed dy. And so what we're really concerned is, what is the integral of dy? And that's going to be y, because this whole piece right here is going to be treated as a constant because it's in terms of x. So it's going to be y times the square root of 2 plus x cubed dx. And this is going to be evaluated from 0 to y equals x squared. So now we just plug in the x squared for y, and we subtract off 0 for y, which is just 0. And we get the integral from 0 to 1 of x squared times the square root of 2 plus x cubed dx. And so now this piece of the process should be very familiar to you. It's the same as in single variable calculus. And for this, let's do a u substitution. So let's let u equal 2 plus x cubed. Okay, so the stuff under the square root. And so du is going to be 3x squared dx, which tells us that dx is equal to du over 3x squared. Okay, so let's plug this in, and we go have the integral of x squared times the square root of u du over 3x squared. So conveniently, the x squareds cancel out, and we end up with 1/3. Pull that out since it's a constant, times u to the 1/2 du. Okay, and so if we integrate that, we end up with 1/3 times 2/3 u to the 2/3. All right, so now let's sub back in our 2 plus x cubed for our u, and let's evaluate. So this is going to give us 2/9 times the square root of 2 plus x cubed evaluated. Let me see if I can draw that in the screen. Evaluated from 0 to 1. And so this is going to be equal to 2/9 times the square root. Okay, so putting in 1 cubed plus 2, and then that's going to be cubed, is going to be 3 cubed, the square root of 3 cubed. And then we're just going to subtract off, subbing in 0 for x, and so that's going to be the square root of 2 cubed, which is going to give us 2/9 times the square root of 27 minus the square root of 8. And when all is said and done, we can simplify a little bit, and we can end up with, we'll end up with 2/3 times the square root of 3 minus 4/9 times the square root of 2, which is approximately 0.526. Okay, so that was it with that one. And keep in mind, if you end up having any questions about any of this, post to the forum, send me an email, and I will address it as soon as I see it. Okay, moving on to our next exercise. We are going to set up and evaluate the double integral that gives us the area of this triangle. All right, so now let's just keep track of what we have going on here. So this would be y, this will be x. We know some coordinates. This is 0, 2. This point over here is 3, 2. Here and up here we have 3, 5. Okay, and yes, it would be easy to geometrically just go ahead and compute the area, but we want to practice setting up the integral. So we have to figure out what the limits are going to be on our integral. So we have to figure out the x and y limits here. Okay, so let's choose one to start with. Let's start with x. So in this case, 0 is going to be less than or equal to x, which is going to be less than or equal to 3. So you agree here, x is going from 0 to 3. So, but the thing is, if we just said that y was going from 2 to 5, that would give us a rectangle. And this is not a rectangle. And so we have to set the outer bound of this triangle. And so we have to determine what the relationship between x and y is here along the hypotenuse. So let's figure that out. And the equation for this line would be given by y equals x plus 2. You could also write it out in terms of x, which would be x is equal to y minus 2. And then let's go through then and say that for y, our limits are going to be from 2 all the way up to x plus 2. Okay, because we care about everything inside this triangle. So our integral is going to be from 0 to 3 times 2 to x plus 2 times, so it's going to be the integral from 0 to 3 and 2 to x plus 2 for dy, because that's our inner one, dx. And remember that dy dx is simply dA. So if you integrate dA, you get the area. All right. So now let's just evaluate. So we start from the inside. And so the area is going to be, so we still have 0 to 3. And then we want to integrate 2 to x plus 2 dy. Well, the integral of dy is just y. We need to evaluate this from 2 to x plus 2. And we still have our dx. Okay? All right, now we need to go ahead and sub in, and this is going to be the integral from 0 to 3 of x plus 2 minus 2. So I'm just plugging in dx, which is going to give us the integral from 0 to 3 of x dx. Okay? And so now, if we want to integrate x dx, that is going to be x squared over 2. And we're going to evaluate that from 0 to 3. And that is going to be 9/2, which is 4.5. So let's just take a step back and look at this to make sure our answer makes sense. So for x, we're going from 0 to 3, so that is a length of 3. And for y, we're going from 2 to x plus 2, or one example would be 2 to 5, so that's another length of 3. And so to remember that the area of a triangle is 1/2 base times height. And in this case, length and height are equivalent to each other. So we could do length squared divided by 2. So that would be 3 squared over 2, which is 9/2, or 4.5. So that we checked our work, so this is correct. And this is where the equation for the area of a triangle comes from. Next, we're going to find the volume of 40 minus x squared minus y squared on the following intervals. So on -1 to 3 for x and -1 to 5 for y. And please feel free to pause and go ahead and try some of these out on your own as well before looking at the answers or watching the answers. So now for x, we're told we're going from -1 to 3. For y, we're going from -1 to 5. And our function is 40 minus x squared minus y squared. And this is going to be dy dx, since our y extents are on the inside and our x extents are on the outside. So this is going to be equal to the integral from -1 to 3. And we want to integrate our function in terms of y. And so this is just going to be 40 times y minus x squared y minus y cubed over 3, evaluated from -1 to 5, and we still have our dx left over. And so this is going to be equal to the integral from -1 to 3. Now let's plug in our 5, and then we need to subtract off our -1. So we're plugging in our 5 for y, make sure. So it's going to be 40 times 5 minus 5x squared minus 5 cubed over 3. And so then we're going to subtract off minus 40 plus x squared plus 1/3 dx. And we just need to simplify that a little bit. So we have not integrated for our x yet, so -1 to 3, and it's going to be 200 minus 5x squared minus 125 over 3 plus 40 minus x squared minus 1/3 dx. Okay, and so we end up with the integral from -1 to 3 of 198 minus 6x squared dx, which is going to be equal to 198x, since we're just integrating for dx here, minus, so it's going to be 6x cubed over 3, which gives us 2x cubed. And we're going to evaluate from -1 to 3. And so we're almost there. This is going to give us 198 times 3 minus 54. So that's plugging our 3 in. Now we have to subtract off, plugging in our -1 for x, which is going to give us minus 198 plus 2, which is going to be 594 minus 54 plus 198 minus 2, which is going to give us 736. Okay, that's it with that one, and we have two more. And once again, feel free, once I actually give you the expression, to try this out on your own. And so we're going to find the value of the integral from 1 to 4. And from 0 to 1. And we're going to have x e to the x squared plus 4. So x squared plus 4 is our power, plus y e to the y dx dy. So in this case, our order of integration is different from what we've been doing. Our y extents are on the outside and our x are on the inside. And so let's take care of evaluating this. So our y is going to go from 1 to 4. Okay, so now we have to integrate this whole piece right here in terms of x. And so we get, so let's see, we have x e to the x squared plus 4 plus y e to the y. And in terms of x, this is going to give us 1/2 e to the x squared plus 4 plus x y e to the y. All right, because remember, dealing with powers here, we're going to end up dividing by 1/2 x. Okay, so then the x's cancel, and we end up with 1/2 e to the x squared plus 4 plus xy e to the y. We're going to evaluate from 0 to 1, and we still have our dy left over. And so this is going to be the integral from 1 to 4 of 1/2 e to the 5th plus y e to the y minus 1/2 e to the 4th dy. Okay, we can simplify that a little bit. And we have the integral from 1 to 4 of 1/2 e to the 5th minus e to the 4th plus y e to the y dy. All right, so here's the thing. In terms of y, integrating y e to the y is going to be a bit tricky. So remember integration by parts? Okay, well that's coming back, and we are going to take care of this piece with integration by parts. So it's going to be y, the integral of y e to the y dy by parts. Okay, and so to integrate by parts, it's going to be the integral of u dv is equal to u times v minus the integral of v du. So we're going to let u equals y, and du is going to equal dy, and dv is going to equal, we'll have it be this piece, the e to the y dy, and v then will be e to the y. Okay, so we end up with, putting these pieces together, our u was y, our v was e to the y. And then we're going to subtract off the integral of v du. Our v, once again, was e to the y. And our du was dy. Okay, so this is going to give us so that's going to be our integral of u dv. And so this is going to be y e to the y minus, and the integral of e to the y dy is e to the y. So we end up with, plugging everything back in, the integral from 1 to 4 of 1/2 e to the 5 minus e to the 4th plus y e to the y dy is going to be y over 2 times e to the 5th minus e to the 4th plus, and then the piece that we figured out up here, y e to the y minus e to the y, which we could pull out in e to the y. We have y minus 1 left, evaluate from 1 to 4. Okay, and then we just plug in our 4 for our y's, and we subtract off plugging in our 1's for our y's. And that's going to give us 2 times e to the 5th minus e to the 4th plus e to the 4th times 3 minus 1/2 times e to the 5th minus e to the 4th plus e to the 0 times 0. Okay, and this is going to give us 3/2 times e to the 5th minus e to the 4th plus 3e to the 4th, which overall can be simplified to 3/2 times e to the 4th plus e to the 5th. And if you wanted to just write that out in numerics, that's going to be approximately equal to 304.5. All right. We have one more to go through together. So let's look at this one. So we're going to reverse the order of integration and evaluate the following. Okay, so we're going to go from -8 to 0 and minus 1/2 times the cube root of y to 1 of the cosine of x to the 4th dx dy. So definitely I'd like you to give this one a try on your own and then resume to see the solution. A practical place to begin on this always is to sketch out the boundary, right? That's step one. Sketch out the boundary we're integrating over. All right, so let's draw a sketch. Y versus X. And so for the Y, we're going from -8 to 0. So this would be Y is -8. And over here, up here, we'll just do Y is 0. Okay, just marking off our bounds here. And then for X, well, we're going all the way up to X equals 1. So that would be, let's just call this X equals 1. All right, but we got to figure out now what's going on. That's the upper limit for X. Now we got to figure out what is going on for the lower limit of X. So we're going to be somewhere down in this region. However, we have, this is going to be X for our lower limit is equal to -1/2 times the cube root of Y. A way that we can write that would be much friendlier to our eyes is that Y is equal to -8x cubed. Just solving for Y. Okay, and so that's going to look something like this. Okay, so this is Y equals -8x cubed. So this is our lower limit for our X. So that's our lower bound for our X, and our upper bound is X equals 1. So we're in this region for integrating. So now we have to go ahead and switch the order of integration. So for X, you can see that we're going from 0 to 1. And for Y, we are going to, our lower limit for the Y is following -8x cubed. And our upper limit for the Y is Y equals 0, since we're shaded in this region right here. So it's going to be the integral from 0 to 1, and that's our X, and from -8x cubed to 0 for our Y, and we still have cosine x to the 4th dy dx. Okay, so starting with the inner integral, okay, it's just going to be Y cosine x to the 4th. And we're going to evaluate this from -8x cubed to 0. Let's not lose our dx. Okay, now let's plug in. It's going to be 0 to 1. With 0 for Y is going to give us 0. Minus a minus, so it's going to give us +8x cubed cosine x to the 4th dx. And so just write that a little clearer. So we're going 0 to 1 of 8x cubed cosine x to the 4th dx. And now we're going to do a u substitution. So let's let u equal x to the fourth, and du then is going to equal 4x cubed dx, which tells us that dx is going to be du over 4x cubed. All right, and so now then we have the integral of 8x cubed cosine u du over 4x cubed. So the x cubes will cancel out and we'll end up with 8 over 4, which is just 2. And so we get the integral of 2 cosine u du. Okay, and so let's evaluate that. So that's going to be 2 sine u, which is going to be x to the fourth, evaluated from 0 to 1, which is just going to give us 2 sine of 1 minus 0, which is about 1.683. And that is all. So that is all for today, and I will see you next time. Have an excellent rest of your day.